to record. Okay, last time I just asked you to solve this problem. I don't need you to calculate the resultant force because we have done it together, right? I need you to find out the acting point. Yeah, good afternoon. I need you to find the center of pressure of the resultant force, but you didn't try it. I know it's a little bit difficult, so although TA already uploaded the solution, let's figure out together today. First, let's recall how to calculate the magnitude of the resultant force for the straight plane submerged in the fluid. Okay. For the straight plane, no matter its shape, we only need to find out the center of its centroid and the pressure at the centroid of the area times the total area of the submerged area. That will be the total pressure force. Okay, we mean the magnitude. Here we got two fluids, right? One is water, another is cement. That means the pressure distribution will not be linear because there is an interface. There is a jump, there is density jump, there is specific jump, and but we can draw the free body diagram, right? For the upper part, which is submerged in the water, its pressure distribution should be triangular, right? Because we know the pressure increase linearly with a vertical distance to the free surface. Sure, here we use gauge pressure. Gauge pressure, that means we measure pressure refer to the atmospheric pressure. The free surface is the atmospheric pressure. So the absolute pressure minus that ambient pressure minus the atmospheric pressure will result in the gauge pressure. That's why at the free surface, the gauge pressure equal to 0, and then it will increase with the depth, with the vertical depth to the free surface, right? So this is upper half, upper part. However, because lower is cement, that means the pressure will, just for example, at any point, for example, this point, the depth, the vertical depth to the interface, the interface between the water and the cement is H prime, and then the increased pressure due to the cement will be gamma 2 H prime, and the pressure at the interface we know is gamma 1 H1, right? At the interface will be equal to gamma 1, the specific weight of the water, times the vertical depth to the free surface. And accordingly, the pressure at this point will equal to the pressure at this interface plus the pressure due to the weight of the cement, right? So we can also draw the pressure prism in the lower part, right? And so it will be a trapezoidal, right? So this is a pressure prism. for the cement section. And this pressure at the bottom will equal to the pressure at the interface plus pressure due to the cement weight. Right. So we can calculate the total pressure force acting on this plate. We can calculate it separately. First, the water part. The water part, well, we know you can use what we have learned last time, well, equal to the pressure at the centroid. That will be gamma 1 half H1, right? The pressure at the centroid times its area, right? The area will equal to the height times the depth. The depth is unit depth, 1, okay? So this part is actually corresponding to the pressure force acting on the water part. Water part, okay? This one is a pressure force due to the water acting on the plate. Sure, definitely. You can use what you have learned in theoretical mechanics. We know this triangle pressure loading, its total force will be equal to the area covered by the loading. Here, we can say it will be equal to the volume covered by the pressure loading, right? Because we have the unit width, okay? So the area by the all in place area in 3D, it will be volume. The volume we can easily calculate the volume, right? Still, the area times the width. The area is gamma 1 h times h1 times h1 divided by 2, right? The triangular area, and then times the width. It will result in the same solution, the same answer. This will be the pressure force due to the water. We should be careful. We also have different fluid. We have cement here. So the pressure force due to the cement, you still can use the formula. The pressure force acting on the plane will equal to the pressure at the centroid of the pressure at the centroid of the plate. Here, you should be careful. We mean it should be the same fluid because here we got two different fluids. That's why we need to calculate it each by each. We need to calculate the pressure force respectively for each part because we have two different fluids. Okay, so here for cement part, for the cement segment, the pressure force will equal to the pressure at the centroid. That will be gamma 1 H1. This will be the pressure at the interface plus the pressure due to the cement weight. That will be gamma 2 half H2, right? This will be the pressure at the centroid. And then times the area of the segment, right? It will result in this one. Okay, so this is we use the formula. That means the formula indicates that the total pressure force acting on a straight plate submerged in a fluid is equal to the pressure at its area centroid times the total area. Okay, we use the formula directly, no problem. Sure, again, we can calculate the pressure force using the pressure prism, using what you have learned in theoretical mechanics. For this trapezoidal pressure loading, its pressure force again still equal to the area covered by the pressure loading and then times width. And how to calculate the area of this trapezoidal? Yeah, you should be quite familiar, right? In middle school, in geometrics, you know how to calculate, right? So anyhow, to find out the total pressure force is not difficult for you, right? However, not only the magnitude of the force, we also want to find out the acting point of the resultant force. How to find the resultant force? We know that we use the moment equation because according to what we have learned before, the moment of the resultant force about any point will be equal to the summation of each element force about the same point, right? So we can here we can use this moment equation for this triangular. We know it's for this triangular for the water part. So this will be the P1, right? The total pressure due to the water, okay? And here, we mean the distance to the free surface will be H1 2/3, right? This is what we have learned before. How about this trapezoidal? For the trapezoidal, we have dealt with it a lot of times, right? We can split into two parts. One is uniform pressure loading, one is triangular pressure loading. For this uniform pressure loading, we know P2 and acting point is centered of this cement segment. So the distance will be half H2 plus H1, right? And for this triangular, again, the same. This will be P3. And its distance to the free surface should be equal to sorry. For this P3 should be 2/3 H2 plus H1, right? I mean, the distance, the vertical distance to the free surface will equal to 2/3 H2 plus H1. So you see, for this pressure loading, we split into three parts. First one is the triangular pressure loading due to the water. And then for the cement parts, for the cement loading, we split into two parts. One is uniform, the other is triangular. And for the uniform pressure loading, we can find out P2. What will be P2? P2 will equal to gamma 1 H1 times this area cap H2. Right, this is P2, and its acting loading is the centroid. And how about P3? P3, well, equal to the area covered by the triangle, and then times with P3 times, P3 will equal to gamma 2 H2, right? Times H2 divided by 2, right? And times 1 is same, right? So P3 is equal to gamma 2H2. Why is gamma 2H2? Because for this one is actually equal to gamma 2H2 minus will be this one is actually the pressure due to the cement hatch gamma 2H2. And so we know the P1, P2, P3, and its acting point, and then use the moment, right? The moment equation, we need to find the total pressure loading P times the distance. We don't know the distance, okay? Well, equal to the, here the pressure loading will equal to the summation of the moment by by each force, right? So we have P1, P1 about this point, okay, P1 times its moment arm and plus P2, its moment arm will be, we already know its moment arm, right? And P3, its moment arm, we already know. Right, and then you can find out the vertical distance of the center pressure. Okay, so please try to figure out how to find out the center pressure, how to find out the acting point of the resultant force of the total pressure force. You need to use the moment equation. Okay, this is what we have learned last week, last Thursday. And then we also introduced how to calculate the hydrostatic forces on curved surfaces. According to what we have analyzed, we just isolate a fluid volume and then we draw FBD. For example, here we have the isolated fluid volume A, B, C, and then we know it will have force by upper fluid F1. It will have force by the left fluid F2, and also it will have force due to the curved surface BC. We don't know the magnitude and direction of the force by curve BC. So we use its horizontal component, vertical component. Actually, we know for curve BC, it's a distributed pressure loading, right? It's a distributed pressure loading by BC, and this will be its resultant force of this pressure, distributed pressure loading, okay? Except F1, F2, and the force by curved BC, never forget the weight of the fluid volume. Okay, nice. Fluid volume have the weight, and then we can use the equilibrium equation, right? Because it's static fluid. So in horizontal or vertical or XY axis, we should have the equilibrium equation. Accordingly, we can find out the horizontal component of the force by the curve BC should equal to F2. F2 is actually the pressure force on the vertical projection AC of the curve BC, right? So how to calculate F2? We just have reviewed that. We know F2 is actually the total pressure force acting to the straight plane AC, and then F2 will equal to the pressure at the centroid of AC. Sorry, pressure at the centroid of AC and times the area AC, right? So when you need to find out the horizontal component for force component, you need to project, find its vertical projection AC, and then find the centroid of the project area AC, and then calculate the pressure at the centroid, and then times the area of AC. After find out the horizontal component of the force by curve BC, we can also find out the vertical component, the force, vertical force component by the curve BC to the fluid volume. What will it be? Again, according to equilibrium equation, right? In vertical direction, we should have with 1 plus W will equal to Fv, right? W is the weight of the fluid volume. How about the F1? F1, because we know F1 is actually AB is horizontal plane. So AB is uniform pressure loading. F1 is equal to the pressure loading times the, right? F1 is uniform, right? Well, equal to gamma H. H will be the depth, the vertical depth to the free surface. Gamma H times the area of AB, right? This will be F1. And from this, it's easy to find out H times area of AB is actually the volume, is actually the volume of the free of that surface AB, the horizontal projection plane to free surface, right? This is the volume, and gamma times the volume actually is the weight of the upper fluid. Okay, this will be the weight of the upper fluid. And then you say F1 plus W, and W is the weight of the fluid volume, and F1 is the weight of the fluid volume for the upper part. So accordingly, from this equation, it's easy to know that the vertical component of the curved surface to the fluid volume is actually equal to the weight of fluid directly above the curved surface. Okay, so this is the volume. Okay, the gamma times the volume will be the weight. This will be the vertical force. You see, for here, we need to know that here we do the analysis. Actually, action and reaction forces, right? Action and reaction forces. So FH, and we will have FH prime, right? And FV prime. That means they are action and reaction forces. So after find FH, after find FV, you can find FH prime, FV prime. And then if the vertical component, the horizontal component, we can find out the total force, right? And not only the magnitude, we can also find its direction, right? This is, we can do, sure, definitely you can use the integration method. You can choose an element area and then calculate the element force and then do the integration. Okay. So this is what we have learned last Thursday. Okay. So here you can see it clearly. This is the fluid volume, the liquid block. We isolated this liquid block. And then this is a curved surface and the vertical projection of the curved surface. This is a horizontal projection of the curved surface. And then we isolated the liquid block with the horizontal and vertical and curved surface. And then we just draw FBD, the uniform pressure loading, and this will be trapezoidal pressure loading, and this one will be the pressure loading and curve surface. And we remind you, and pressure will be always perpendicular to the surface and point to the surface, okay? And so for this pressure loading, we can find its resultant. And then with this resultant force, we don't know its magnitude, we don't know its direction. So we use its horizontal and vertical component. Okay, and then we calculate horizontal and vertical separate respectively. Okay, that's like here. Okay, so this is the curved surface, right? And then for the curved surface, for the acting force on this curved surface, we still use the isolated fluid block, right? And then draw FBD, and then we can find out the horizontal force. The horizontal component is actually equal to the force on the vertical projection area. Okay, horizontal force is equal to the pressure force on the vertical projection area that will be equal to the pressure at the centroid of the projected area and times the area of the projected area. And the center pressure of HR, or the acting point of the horizontal, will be called the central pressure. We just find out, right? We just find out how to find out using the moment equation. And the vertical component still equal to the weight of the liquid volume above the curved surface, right? This one we know we can calculate it. We can do it again and again, right? So here we have introduced the atom pressure volume. We should know the pressure volume is actually just geometrical terms. It does not necessarily really got liquid inside. Okay, for this one, we call it true pressure volume because we got real fluid above. Why? Because here for this curve BC, curve AB, we can just know if we want to find out the vertical component, it will be equal to the weight of the fluid volume. Why? Because again, we can do this. This will be ABC, and then this is pressure loading, right? You can do it by yourself, and then this will be the pressure loading trapezoidal, right? And this is a vertical projection, this is a horizontal projection, and then we use the horizontal and the vertical component. We decompose the horizontal force of the curved surface, and then its weight. So again, the horizontal will equal to the force on the vertical projection area, the centroid. Okay, this will be F1. We still have F1, and vertical still equal to the gamma volume. Why? Because it could W plus, this will be F2. Okay, gamma plus F2. F2 is equal to the weight of this fluid volume. And so FV is still gamma volume. Volume is actually the liquid above the curved surface. Okay. However, for this, for figure A, yeah, it's easy to find out. For figure B, we find out. So again, sorry, I forgot to mention that for the force acting on the curved AB, the FV should be downward, right? Right, the FV should be downward. I mean, the vertical force by the fluid on the curve AB should be always downward, right? Should be downward here, right? However, for this case, we draw FBD for this fluid block. We isolate it with the projection area, horizontal and vertical, and then you still can draw FBD, right? Here is still uniform pressure loading, right? And this one we still use horizontal and vertical. Okay. Again, here, remind you, here FV is actually the force by the curved surface to the fluid. So according to action and reaction forces, so the force by the force by the fluid to the curved surface should be Fh prime, Fv prime. Okay. And here again, still Fh. This will be F1. This will be sure. So F2, F1. Okay. Fh so still should equal to F2. So that means the horizontal component still equal to the force acting to the vertical projection area, right? And you know how to calculate it, right? You use the pressure at the center of the vertical projection area and then times the vertical projection area. We can find out the horizontal component of the force to the curved surface. And for the vertical part, for the vertical component of the force to the curved surface, what will be? In vertical direction, we will have F1, because this is W, right? F1 minus W. Well, equal to equal to Fv, right? So here we can find out still Fv still equal to the weight of this shadow, right? Still equal to the weight of the fluid volume above the curved surface to the free surface. But here we don't real fluid here. That's why we call empty pressure volume. Okay. So any question about this part? If no question, we will go on. Okay. True pressure volume, that means we got real fluid inside this fluid block. But empty pressure volume here, we don't have real fluid there. And so can you do the analysis of curve ABCD? Here we got curve AB, BCD, and we need to find its horizontal and vertical, because you can't find out the resulting force directly, right? You can find out the horizontal component and the vertical component, and then you can find the magnitude and the direction, right? First, how to find out the horizontal? The horizontal component should equal to the pressure acting on the vertical projection area. What will be the vertical projection area? The vertical projection area will be A prime D, right? Should be A prime D, right? If you are not sure, you can just for this A, B, B, C, D, you can cut into two halves. So for A, B, right, you can find out, right? For AB, this will be B prime, right? And you know, so for AB and its horizontal will be equal to the pressure force acting on the vertical projection area of curve AB. And for BCD, you can do the same, right? So for the horizontal force, it's easy because it will, well, be equal to the pressure force acting on the vertical projection area. And this vertical projection area is straight plane. It's easily find out. How about the vertical force? The vertical force for AB, B, C, D. For AB, what will be for AB? For AB is true pressure loading or empty pressure loading. I mean, whether there is real fluid. No, there is no real fluid in the volume above the curved surface to the free surface, right? There's no real fluid. And we know the horizontal should be upward, right? Sure, if you still can't understand this, we can still isolate the fluid block this way, and then you draw FBD, right? You can still do the same way. So we can find for AB, the vertical force actually equal to the weight of this empty pressure volume, right? And it's upward. But however, for BCD, how to calculate the vertical force by BCD? BCD, this time maybe is better to cut it into two halves. Why? We can do it later on, or we'll know it later on. And for BC, we know for the BC, the vertical component force on the curve surface should be equal to this one, right? Should be equal to the weight of the pressure volume. This is empty or true pressure volume. Got real fluid there? No real fluid. So it's empty pressure, right? Sure, if you don't follow this, you still can isolate fluid block BC and its horizontal projection area and its vertical projection area, and then you draw FBD and you find out the vertical component again is equal to the weight of the empty pressure volume. Okay, for DC, okay, here is empty, but however, for DC, how about DC? We still can do the same procedure for fluid block C prime D, and we find out for BC it's up, but for CD it's downward, and why's downward for DC? For block volume C prime D, still you can draw FBD. You can find out the vertical component of the force on the curved surface DC is actually equal to the weight of the pressure volume. This time it's true pressure volume. We got fluid inside, right? Or maybe we can just do the analysis again here, okay? For C prime D, okay. So for this fluid block, we have the pressure loading. It's uniform pressure loading on its horizontal projection area, C prime, and we have the toroidal pressure loading on C prime D on its vertical projection area, right? We have its weight of this fluid block. For DC, again, we have its horizontal and vertical component. So again, because fluid is anesthetic, we have equilibrium equation. So we have, this is F2, this is F1. So horizontally, we have H equal to F2, right? And for this vertical projection area, because it's straight plane, so we know its total force will equal to the pressure at the centroid times the area. So it's easy for the horizontal part. How about the vertical? The vertical part, we know in vertical direction, we will have F1 plus W equal to FV, right? This one should be okay, right? You can follow this, right? F1 plus W equal to FV. F1 is actually the pressure force due to the uniform pressure loading. And F1, we know F1 is actually equal to the pressure loading, uniform pressure loading times the area. The pressure loading is actually equal to gamma H1. H1 is actually the vertical distance from CC point to the free surface times the area. Okay, so again, this is actually the weight of the fluid volume from CC point to the free surface. And never forget you need to plus the W, the weight of the fluid block. So finally, we just got the conclude that the vertical force by the curved surface to the fluid block is actually equal to the weight of the fluid block above the curved DC to the free surface. Again, action and reaction force. We know the force to the curved surface DC is equal to the weight of the pressure volume of the fluid volume above the curve DC to the free surface, right? And so here you see BC, let's draw it. So BC, we know BC is empty pressure volume. For curve BC, the force is up, right? It's empty pressure. For DC, let's use another color. It's very easy. For curve DC, so the vertical component should be equal to the weight of its true pressure volume and its downward. So we say this part cancel, right? This part cancel out. And so for curve BCD, the vertical force should be equal to the weight by the curve BCDB. Okay, right? That you say why we just need to split curve BCD into two halves, because BC we got two empty pressure volume, DC we got a true pressure volume. Okay, that's why. So now it's your turn. Please draw the pressure volume of curve ABC. Here, careful, you got water on both sides. Left side, you got the water and its depth is D, and right side, you also got the water and the depth is half D. And please do it by yourself, and then we will figure out together after 10 minutes break. Okay, so 10 minutes break. And you need to figure out, and then I will ask somebody to help me to do this.